Right, let's go. So, welcome back. So, what we missed last time, if you didn't catch me on Tuesday night, I did record the async lecture. So, if you're like me and don't refresh very often, refresh the website, and of course, it's going to take a while. Come on, man, messing up my timing. And the lecture recording is right here. This will take you right to the live that I did. So, and I'm not logged into YouTube on this machine, so I got an ad. But that'll take you right to the recording. I did go live for it just because it was simpler logistically for me to go live, even though most of the time I was just talking to myself in the computer. I went live for it, so it takes you to that live VOD. So if you look at the VODs, we are a little out of order because it'll go lecture 10, then today lecture 9, which I think you'll be okay. Y'all can figure that out. So today we want to talk about graphs, and since the async lecture is recorded, this is the last time I'll be going live this summer. Right after this lecture, I'm going to tear down my green screen and and convert my studio back to regular office. So let's do it. The summer goes fast. I said that a bunch, and yeah, here we are right at the end. So last time we had the midterm on lecture 9. Sorry about that little, we had a little issue at the beginning and had a rough start to the midterm. I did extend the time. Hopefully you all saw that I extended the time to 1:50 to account for the lost time. I think we lost about 10 minutes at the beginning, so I gave you 20 minutes just to make up for that. When will you know the results of the midterm? That's what I'm talking about right now. They are posted. You can go to Autolab. When you go to Autolab now, I'm signing into Autolab, you'll see all the results for the 4 traces and all of your results, the feedback. When you click on your score, it'll give you the feedback. It'll give you a link to go to the tracing tool, and you can see what you submitted on the tracing tool as well. So you can go back to, so you can take a look at everything. So results are out. For those of you who like stats, I think I have a few stats for y'all. Was it 29 students did complete both learning objectives and do not have to take the final. So just a reminder, you need to pass either one of OOP 1 or 2 or and one of DS1 or DS2. So you have the 2 learning objectives, OOP and data structures. You get 4 traces, 4 chances to pass each one, and you only need to pass 1 trace in each category. The first 2 in each category are in the midterm. The second 2 of each category are on the final exam. Final exam, if you do need to take it, has the same structure as the midterm, but if you passed, say you passed OOP 1 and failed the other 3 traces, that means you're done with the OOP learning objective. And when you go to the final exam, you don't have to take either of the OOP traces, but you do need to take the data structures traces because you do need to pass one of those in order to pass the course. So for the remaining 21 students who did not pass at least one of each category of trace on the midterm, you do unfortunately have to go into the final, and it is do or die. It will. I don't like high stress exams. That's why I have multiple opportunities for everything. But if you didn't make it on this first opportunity, you do unfortunately have a high stress exam because your whole grade is on the line on the final exam. Out of those 21 students, I think just looking at what they've done throughout the semester, which is for some of them very little, for some of them it won't even matter. Even if they pass the final, they'll still fail on problem set points. So it's a pretty small fraction of the course who is going to have a high stress final, but it's what it is. But yeah, so take a look at your grades. These are posted on Autolab with either a 1 or a 0 to say if you passed or failed that trace. When you go to the tracing tool and look at your trace, the grades are out of 5. That's so we can give you more granular feedback. So if you passed the trace and you got a 5, that just means you did awesome on it. If you got a 3 or a 4, we did still consider that a pass for the learning objective, but that does mean you should go back and study tracing, that you are missing some aspects of tracing that you really should brush up on to make sure you know the stuff. If you're weak on tracing in 116, it will be pretty tough going into 220. Tracing is the biggest pre-220 topic that we cover here. Obviously, we cover a lot of data structures that leads right into CSE 250. But the tracing, I'd say, is the biggest thing that will help you for 220. So if you passed both of these on the midterm, but you got 3 out of 5s on your traces, just make sure you brush up on that, or else 220 is going to be a tough time. So midterm grades posted. We have the problem set 3 deadline tonight. I assume you're all aware of this. We have a pretty good rhythm in this course. Every Thursday night is a deadline. So I'm sure you're all aware of this one coming up. And then after today's lecture, you'll have everything you need for problem set 4, which is due a week from today. Which for a lot of you, for 29 of you, this is the last thing you need. Well, that's not really true. A lot of y'all didn't do PS3 yet. You wait until tonight, apparently. Oh, I was going through stats too. And for stats, 4 students in the class have already earned an A, and they're done. They're just done with everything. One of those students even got 50s on PS0 through PS3, and they don't even have to do PS4. They already have an A without PS4. Let me hesitate a little bit there. No, sorry, I am misspeaking. I'm thinking the other side. Sorry, 230 is an A. I'm like, that doesn't make sense. I wouldn't let you skip a problem set and still get an A. Yeah, I'm thinking of a different grading structure. So 2 students already have A's and don't have to do anything else in the course. Not 4, 2 students. And yeah, sorry, that one student, sorry to get your hopes up if you're listening. Yeah, you do still need to do problem set 4, unless you're happy with a B, of course. I would assume you're not. If you maxed out your points on the first 4 problem sets, you're going to go for that A, and you're going to get it. Okay. So any questions about logistics, I'll still be watching chat to catch those. I think that's everything I wanted to say before we get into content. So let's get into content. All right, graphs. And this, usually in the fall and spring semesters, a lot of students take 191 alongside 116. That's how the flowchart wants you to do them, and most students abide and go the typical route. So when you're taking 191 alongside 116, graphs are usually like right next to each other. I think 191 usually covers it a week before 116 does. So if you already took 191, you've seen quite a bit about graphs. You know a lot of what I'm going to say, but I do, have to, but I'm going to start right from the beginning, assuming that you know nothing about graphs, because some of you didn't take 191. It wouldn't really be fair if I'm just like, you know what graphs are when you don't know what graphs are. If 191 was a prereq, I wouldn't do this, but 191 is not a prereq. So we have to talk about what a graph even is. So let's talk about graphs. So graphs are a data structure, which is kind of wild because we already have a whole bag full of data structures. We already have 4 different data structures, 6 if you count stacks and queues, 7 if you count BSTs. And like, do we really need another one? Like, what are we doing here? Well, we already have arrays. This is arrays and linked lists are sequential based data structures. And I want to do an overview of just all of them that we've seen, just to justify why we even are talking about graphs. Why do we need another one? So we have our sequential based data structures, array list and linked list, or arrays and linked list. If you did watch the lecture 10, the runtime lecture, I did a lot of analysis on the runtimes of these, comparing specifically with prepend and append, the differences between array list and linked list performance. They're both sequential data structures, meaning that they keep track of the order of the elements in the data structure, but they both have pros and cons in terms of efficiency for specific problems. Specifically, if you want to append to the end of a data structure, an array list is really efficient with that. If you want to prepend to the beginning, then a linked list is very efficient for that. And there are ways that we can work with linked lists, like we did with a queue, where we can store a reference to the head and the tail of the linked list and get efficient append and prepend, and removing the first node and removing the last node. We can do all that very efficiently in O of 1 time. But we don't have random access. We can't just, given an index, get the value at that index in constant time, we have to do that in O of n time to be able to traverse the linked list. So a lot of trade-offs, but at the end of the day, they're still both sequential data structures, so they do accomplish the same task. They're the same thing, just different efficiency, but they do the same thing. Then our first non-sequential data structure was a map or a dictionary in Python. When you were introduced to this, it was a dictionary. If you took 115, and this is our key value pairing. A key value uh, a key value store is usually what we call them, where instead of storing values in a specific order, now we're creating an association of keys to values. So we store some value at a key, and the keys can be anything that we want them to be. They don't have to be indices 0 to n minus 1. They can be, in this case, strings or ints or really whatever we want. Not doubles though. Don't I don't know if this ever comes up in 115 or 116, but you don't want your keys to be doubles. Now, and we have everything we need to understand why that is the case. You absolutely can like physically create keys as doubles, but since you have truncation errors with your doubles and the keys need to match exactly, you'll get some really weird bugs if you have doubles as your keys, because once a truncation error hits, you're going to have value key not found in your key value store, even though there is the key, but you just have a small truncation error, which makes it makes you not able to find that key. So you wouldn't want doubles. Technically you can, but it's not a good idea. So you can have whatever you want with your keys and associate them with these values. Then we had our first branching data structure or nonlinear data structure in a tree, where we don't have our values stored in a specific order, except with a BST when we did an in-order traversal. But we don't have necessarily any order to these nodes, but we do have some structure, but we have this branching structure. And the key point of having a tree is that if we're careful with our tree, then the height of our tree is log of n, and most of our algorithms can be written to be log n efficiency, which is extremely efficient. So a tree gives us a huge advantage in runtime for many of the common tasks that we want to do, specifically when it's a BST, a self-balancing BST. Insert, remove, find are all log n, and we can't get that type of balance with our array lists and our linked lists. Some operations are O of 1, some are O of n, but with a tree, we kind of balance that all out and say, you know what, we can do just about anything in log n, which is pretty damn awesome, pretty damn efficient. So it's a very nice data structure, specifically when it is a BST and you're storing things in sorted order. So where's a graph come in? Well, there's certain data that just doesn't fit into any of those data structures that we just talked about. And we really haven't worked with any data of this structure. So let's talk about it. We have here a map of rails in New York City. And rails can be thought of as a collection of stations, and many of those stations can be connected by rails. So we have the stations that you're interested in that you want to travel to and from, and then rails connecting some subset of those pairs of stations. And then you would travel station to station, taking the rails to be able to get to your destination. Same thing with a highway system. You can think of this as a series of intersections connected by roads. Not all intersections are connected to each other, but you start at one intersection and you want to travel intersection to intersection. If you do, punch in your GPS and try to figure out, or Google Maps and try to figure out where to go, it's going to say go from this intersection to this intersection to this intersection by taking these connected roads. It's not how we think of it when we're actually driving. We just think about our next turn, but that really is how the data is represented, is intersections, and some of the intersections are connected by roads. And the third example, this is the one we'll stare at for this entire lecture, because it's the simplest one. I'm not going to use examples with huge amounts of data. We got a much smaller one. This is the early days of the internet, back when it was still called the ARPANET. And these are locations connected by cables that are connected over the internet, or ARPANET in this case. So we have a handful of locations which were all universities at the point. Is all universities sharing research data. That's how the internet initially started. And these universities are connected with routers and cables to be able to communicate with each other. We only need one OOP trace and one DS trace to pass the midterm and not take the final rate. Yes, that's correct. And I will, this came up in the last lecture, I will send an email probably later today. I guess there's no reason to wait. But an email just confirming with everybody what you need to do for the final exam, whether you need to come and take OOP, take just OOP, just DS, both of them, or neither of them. I'll send out 4 batches of emails to everybody, letting you know your exact situation. Because, I don't know, it's not too complicated, I don't think, but at the same time, I get tons of questions on it, and it's way more complicated than any other course. So I just want to make sure I send out those confirmations and let everybody know exactly what situation they're in. If you're one of those 29 who don't need to take the final, etc., probably later today. I gotta do it before the final, of course, but yeah, I don't think there's any reason to wait later today. Okay, so this is the data that we want to analyze here. And of course the answer is going to be graphs. The whole lecture is called graphs. But let's try to use what we already have to be able to work with this data. And since there's no real order to these nodes and there's no real mapping, I don't see how an array list, a linked list, or a map is going to help us here. So let's try our only nonlinear data structure, our trees, and see if we can get this to fit in a tree-like structure, because it does feel like a tree structure. So let's try that. So let's pick one of these nodes. I always do that. I didn't define a node yet. Well, I guess we did with linked lists and trees. So yeah, I guess I can get away with that, right? So UCLA, let's pick a node, and just arbitrarily, I just decided to pick UCLA. And let's try to jam this into a tree data structure. So UCLA, I'm going to say all of the nodes that it's connected to, let's call those child nodes of UCLA. So we're going to pick UCLA as the root, and then it has Stanford, SRI, RAND, and UCSB as its child nodes. Good start. I'm fine with that. And then we have to go to one of the child nodes. Let's go to Stanford. And Stanford is going to have SRI and UCLA as its child nodes. So we have UCLA and SRI as the child nodes of Stanford, and we immediately run into an issue. Here we have Stanford as with UCLA as a child and UCLA as a parent. Like, that's kind of weird, and we're obviously going to go infinite here. UCLA, when we visit it again, is going to have Stanford as a child, which has UCLA. We're going to go have an infinite size tree, which we can address. We can just say, well, if that node is your parent node, have each node store a reference to its parent, and say if a node is your parent node, don't also make it your child node, because we're going to go infinite. The problem with that is we also have SRI as a child node. In SRI, it's not immediately obvious that this is going to be a loop, but SRI is going to have UCLA, then Stanford, SRI, UCLA, Stanford. And we're going to keep going around in this circle. And this is the big difference that we're talking about now, is that a tree cannot handle these cycles. A tree can't handle a cycle. So once you have this loop that you can travel around, a tree is not going to be a suitable data structure anymore, because your algorithms are going to go infinite, your trees are going to go infinite. If we did somehow just say Stanford has the existing SRI as a child node, and we try to do an in-order traversal on this tree, we're going to still go in loops around that cycle, because we have Stanford to SRI to UCLA. We have that cycle and no way to actually stop it, because our algorithms just aren't suitable for that. So we have repeated data and these cycles that are going to break our algorithms. So let's try that. Let's try what kind of what I just described. Instead of Stanford having a new node for SRI, let's link it to the existing SRI, which can be fine. Like, we can do this, and in fact we will do this. This is what we're going to do. Have it linked to the existing SRI, and then build the entire data structure that way. But the problem is those cycles. So these cycles in the data structure eliminate this from being able to be a tree. And all of our algorithms break because our tree algorithms just aren't suitable for this. They're just not made for this. They're expecting two child nodes of null to indicate that we hit a leaf node and then return up the recursion. So this is a new data structure, and this is our graph data structure. So we have nodes, and all those nodes can be linked via edges. This is our data structure, and it can have cycles. So cycles are allowed in a graph, and we're going to have to be aware of that in all of our algorithms and be able to take that into account. Whenever we're writing an algorithm that works on a graph, we have to make sure we don't get stuck in a cycle and go infinite. Because all of our recursion that we use with trees, it's going to go infinite. And the way we store these, so this looks like a node-based data structure, and in fact it is. It is a node-based data structure. But the way we represent this in the code is going to be a little bit different. We're not going to have each node be its own object. We actually could do that. There's nothing really stopping us except the code would be extremely gross and bloated. But we're not going to do that in the code. Instead, we're going to have two separate data structures that are going to store the nodes. So we're going to have a list of all the nodes and then a list of all, oh, that's actually not how we represent it in the code, in the repo, is it? But we're going to store all of the nodes. I'll explain in a sec when we see the code. We're going to store all the nodes and then store all of the edges as well. So we need to store all the nodes and edges of our graph. Where a node, we're used to thinking of nodes, but here it's not going to be node objects. We're not going to have a node class. We're just going to have a graph class that's going to know about all the nodes. And each node is a piece of data in our graph. And then an edge is a pair of two nodes that connects those two nodes via that edge. So we can traverse all these edges to be able to get to from one node to another if they are connected via an edge. So this is a bit different than our linked lists next reference and our trees left and right references. Here we can have any connections between any two nodes pretty arbitrarily. And there's no real structure, oh, that's a weird way of saying that, but there's no real structure of a graph. And what I mean by that is UCLA looked like the root node of the tree, but there's no such thing as the root node of a graph or the first node in a graph. It's all just an amorphous blob of nodes. There's no special node that is the first node or anything. We just have a graph, and that's it. It's a graph. It's a collection of nodes and edges. That's what we get. No special nodes. And there are two different major ways to represent a graph. Adjacency list is the one we're going to use, and I'll talk about that quite a bit. But the other one, I don't even have pictured here, but I just want to explain briefly. If you took 191, you've heard about both of these. But just so when you see these in the future, you're not like, what the hell? That's not the way Jesse showed me how a graph is represented. But the other one is an adjacency matrix. An adjacency matrix is an n by n matrix. So a two-dimensional data structure. And in each cell, you can think of it as a table, well, it's a matrix. You should know what a matrix is by now, right? Taking a bunch of math classes. And in each cell, it's either true or false. Is there an edge connecting these two nodes in this graph? So we have an n by n data structure. So for all n squared possible edges, we have a Boolean to say whether that edge exists in that graph, connecting those two nodes. And that's a fine way of representing a graph, but it can waste a lot of space. It wastes a lot of memory if you have what we call a sparse graph, where very few of the n squared total possible edges. It's actually not n squared. It's n squared minus n over 2, I guess, for our purposes. And And if you have very few edges, far less than n squared O of n squared edges, then it's a pretty big waste of space, waste of efficiency. Also, they're kind of gross to look at on a slide. So, and they're a bit tougher to work with. They're not bad. It's not impossible or nothing, but a little bit tougher to work with marginally for our purposes. So, what we're going to use is an adjacency list. With this, instead of tracking every single possible edge and saying whether it exists or not, instead we're going to say for each node, store a list of all of its neighbors. So for UCLA, I have a list of every neighbor of UCLA, where neighbor means that those nodes are connected via an edge. So UCLA has Stanford, SRI, UCSB, and RAND as neighbors. So if I look in my adjacency list and I say, hey, UCLA, who are your neighbors? We're going to get those 4 nodes as the neighbors of UCLA. And we do this for every single node. We keep track of all of its neighbors. And this is what we get in the code. When you're coding with graphs, we're going to work with this adjacency list because we're not going to have a good visual of what the graph looks like. On a slide, sure, we have this nice visual, and we as human beings can just look at this and figure it out. When we're coding, we need a more structured way to represent our graphs, and that's going to be an adjacency list in CSE116 at least. We're going to use adjacency list. And notice that every edge in the graph is in the adjacency list twice. So UCLA has SRI as a neighbor, for example. That means SRI also has UCLA as a neighbor. So this SRI UCLA edge is in this adjacency list twice. So every single edge is in this adjacency list twice. So we have twice as many values here as there are edges in the graph. The reason for this is we're using what's called a bidirectional graph, or just a graph. And they're more, I don't know, I guess anything that's more common, that's what gets the default name. Like a method, instead of calling it a non-static method, it's just a method, and then static is more rare, so that we have to say static method. Same thing here. So every edge can be traveled in both directions. If there's an edge connecting UCLA and UCSB, we can go from one to the other and vice versa. There's also a type of graph called a directional graph or a digraph, where that's not the case, where you would have arrows on your edges indicating the direction it can go. This would be equivalent to the traffic example, where some roads are one-way roads. You can only travel in that one direction. You cannot go back to the node where you just came from. In that case, then every edge would not be duplicated. You would only have it, like if it's only UCLA to UCSB, we'd have UCLA, UCSB as a neighbor of UCLA, but UCSB would not have UCLA as a neighbor because you can't travel in that direction. So this is only the nodes that you can travel to. And when I said briefly with an adjacency matrix, like for our cases, an adjacency matrix, every pair of nodes is in that matrix twice, and it defines which is the from and to direction, the direction of that edge. For our purposes, the matrix would be symmetrical because you would always have those two values either both being true or both being false. Is the edge there or is it not? But you can represent a directional graph with an adjacency matrix by not having it symmetrical and represent all that information. And the minus n, if you're really paying attention, the minus n was, it doesn't make sense to have a node that has an edge to itself. Unless that's your specific situation, very specific thing that you're doing, maybe that makes sense. But in general, it doesn't really make sense to have the diagonal of the matrix mean anything. Okay, but this is how we're representing things. And in the code, it's going to look like this. And this is actually the only slide of code I'm going to show in this whole lecture. A lot of this graph lecture is me telling you how graphs work, and then your task is to code that up. Specifically, when we get to breadth first search, that's where we're headed. I'm going to show you everything about breadth first search, how to run it, how to use it, and everything. But it's going to be up to you to code it. I'm not going to show you a single line of code about breadth first search. That's your task for problem set 4 for the last few methods, is coding up the breadth first search that I explained in the code, but never, or explained in the slides, but never showed you the code for. So that's where we're headed in this lecture. So this is the only code I'm going to show just how the graph itself works. And that adjacency list that we're storing, we actually get to combine various data structures. And we are going to talk about a lot of different data structures in this lecture, which is part of what makes me really happy about having graphs as the capstone data structure of CSE116, is we get to flash back a lot of the other data structures that we've seen. Here we're using hash map and array list. So to get this adjacency list, we have a hash map where the keys are nodes with some type parameter. The keys are nodes, and the values are array lists of nodes. So if we go back to the previous slide, we have our map. This is a hash map of nodes to an array list of nodes. That's how we're representing this data in our code. So we have a hash map of nodes to an array list of nodes. That's our adjacency list. We have a constructor to initialize that, which we don't necessarily need. We could do adjacency list equals new hash map, except it would really crowd out my slide because that line gets too long. So we'll put this in the constructor, initialize the hash map to an empty hash map, and we have an add edge method. We're actually not going to use this in 116, so I'm going to skip over it. This is if you want a directional graph, you would use add edge. For our purposes, all of our edges in lecture and the problem set will be bidirectional edges. So this is the one we're really interested in. We're just going to add the edge in both directions instead of just one direction. So it's a non-directional edge or bidirectional edge. When we add an edge between two nodes, we're going to do something called lazy initialization, which actually I might jump to IntelliJ in a second. There's something else we need for the problem set, but we'll do lazy initialization. We add an edge by defining the endpoints of that edge in two nodes, and then we're going to add the node to the graph. So notice we don't have a public add node method. This is private. In the code, before I say something wrong, let me just check. I should have made it public. Hopefully I did. Add edge, add node. No, I did leave it private. Oops. Let's go on a little detour for a second. Maybe I changed it in the handout. Yeah, public add node. So in the handout, add node is public because we do have a situation where we want to, well, add a node. So let me explain what I'm talking about here. So let's go through this code, finish going through this code, and then I'll explain why I was just double checking. So we're calling add node. So once we add an edge, we're going to call add node, which is going to do lazy initialization. This means we're going to initialize our nodes at the absolute last moment possible and then use them immediately after. Very common practice in programming. It helps when you have some situation where you have a lot of possible usages of your data, and if you pre-initialize every possible usage and then you only use like 5 of them, you just wasted a lot of time and memory, and your runtime is going to go in the tank. Instead, we'll lazily initialize, so we'll initialize only when we need something, and that's going to usually speed up. And the very worst case, where we do actually need everything to be initialized, we're at least spreading out the initialization cost and not having a big upfront load time cost of our program. We have it spread out throughout the whole runtime. So a very common thing to do. So we're going to use lazy initialization. We're going to say if we have not initialized this node yet, which means the adjacency list will not have that node as a key. So if we don't have this node as a key, that means we've never added an edge with this node yet. And if that's the case, we're going to insert a key value pair into the adjacency list for this node with an empty neighbor list. So we're going to add this node into the adjacency list and initialize array list to an empty array list. We're going to do that with both our nodes, and then we're going to go to our adjacency list and add each node to the other node's neighbor list of neighbors in the adjacency list. So we're going to get the value at node 1. That's going to give us the array list for node 1, which may or may not have just been initialized. So if add node is called and the node has already been initialized, the condition is false and nothing actually happens. So node 1 might have 100 neighbors already, or it might have just been initialized. We don't know, we don't care. As long as we've called add node, we know it is initialized. It's been initialized at some point in time. Might have been a millisecond ago, it might have been hours ago. We don't know, we don't care. We just know that this will exist. So this dot operator right here will not give us a null pointer exception, and we will not get a key not found exception. We're not going to get any of those errors because this has been initialized because we just called add node. And then with that array list, we're going to call the add method and add node 2 to it, and vice versa, add node 1 to node 2's adjacency list to get this edge captured in the code. There's one downside to the code that's shown on screen, is that we cannot add a node with no neighbors. We just can't do it. It's because mostly because add node is private. So for the handout, we do have situations where we want to create nodes that don't have any neighbors at all, especially in your testing. Well, exclusively in your testing, I suppose. In your testing, you want to create test cases where there are isolated nodes that aren't connected to any edges. So for the handout, I changed add node to public, so you can add a node, get an empty adjacency list, and then never add an edge for that node. That will be useful for your testing. You'll have to have isolated nodes as some of your test cases. Then our sample usage, create a graph, add a bunch of bidirectional edges, and there you have the graph. This is the code that creates the graph that we're using as the lecture example for every single edge. Add it. We don't have any isolated nodes. We don't have to call add node directly. Add node is going to be called by add bidirectional edge. That's going to get all of our data in our graph. Okay, and like I said, that's the only time I'm showing code. This is how we work with a graph in our code. There are a few extra methods here in the handout, mainly a get adjacency list method, because, well, you're going to have to work with that adjacency list in your code, which is outside of the graph class. So we need to get that adjacency list, and that adjacency list has all of the information of the graph, all the nodes. If you iterate over all the keys, that gives you all the nodes, and you have all of the edge information by checking all of the neighbors of every single node. Okay, that's the code. We're done with code. We're going back into the world of theory after that. I guess not necessarily theory, concepts though. Going back to the world of concepts, all conceptual. Okay. Even that's not true. I'm showing examples. It doesn't matter. I'm not showing code. Is the accurate way of saying it. So, oh, excuse me. Oh. So let's get a definition out there and talk about paths, because we have to start working with this data. We have our graph set up with an adjacency list, and we have the code, a class that has the structure of being able to work with that adjacency list. Now let's start thinking about what we want to do with our graphs. Like, what do we actually want to do here? For that, we're going to need some definitions. Let's start with path. A path in a graph is a series of nodes where each subsequent pair of nodes are connected by an edge. So this UCLA, SRI, Utah, MIT, BBN, RAND, this is a path in this graph because I can travel across this path by following edges. So UCLA to SRI to Utah to MIT to BBN to RAND, I took an edge every single time I traveled to the next node. SRI, Utah, BBN is not a graph. SRI, Utah, that's fine. Utah to BBN, there's no edge here. And just because we can go through MIT, that doesn't count. You have to be able to go from Utah to BBN directly if you're trying to define a path, SRI, Utah, BBN. You can't just go jump over here. Or else our paths, if I want to go from UCLA to Harvard, my path would just be UCLA, Harvard. And that's just not interesting to anybody. Like, that's not useful. You just do start node, end node, that's my path. Well, technically there is a path, so I don't know, figure it out yourself. No, a path we want to define every single step of the path. It's like in your driving directions and they're just like, go to your destination. You need to define every single step to get to that destination. And breadth first search, what we're going to spend a lot of our time on, I'll go through. I want to go through the problem set. I haven't gone through the other problem sets, but today there's the way lecture is structured. I'll have time to go through the problem set. I think I'll do it right after this run of breadth first search. So I'm going to introduce breadth first search, and we're going to go through breadth first search 4 separate times. 4 times I'm going to give an example of going through this specific graph using breadth first search. So the first time we're about to see it right now, it's going to be really hand wavy. It's going to seem kind of like magic. I mean, that's not a good way of putting it. It's gonna seem simple actually, and probably make a lot of sense. I hope at least. But it's not going to be clear how you would code this. So as I go through, I want to slowly build you up to being able to write the code that's actually going to perform breadth first search. And the first question that I have is, how do we even check if a graph is connected? Breadth first search is going to help us figure this one out. So how do we check if a graph is connected? A connected graph means that any 2 nodes, there exists a path between those 2 nodes. And we just defined what a path is. So you can travel from any node to any node. That's a connected graph. So how do we tell if a graph is connected? Well, we just look at it, right? You can all tell that this graph is connected. But if we remove a few edges, again, we can just look at this and tell that this graph is not connected. And we define a connected component as a group of nodes that are all connected in a graph. So if a graph is connected, it has one connected component. The entire graph is a connected component. Once we have a graph that's not connected, we can ask how many connected components there are. What are the connected components? So this graph has 2 connected components, one with these nodes up here, and then another one with these nodes down here, and they are disconnected from each other. So how would we tell that this node is disconnected and that there are 2 connected components? Well, again, we're just going to look at it, right? We're just going to look at it. It's right there visually in front of my eyes. I'm going to say it looks like 2 connected components. Problem with this is that the internet has gotten quite a bit bigger over time. Once we have a lot of data, which is really the only thing we're interested in, I shouldn't say the only thing, but mostly what we're interested in is what happens when we have a lot of data. If there's a small amount of data, like, do we even need a computer or computer scientists or programmers? Like, if we have a small amount of data, we're just gonna, do things manually. It's gonna be easier than writing all the code and learning all this stuff that you're learning over 4 years. It'd be easier just to do it manually. Problem is, once we have, or the excitement, really, the way I look at it, is once we have a lot of data, well, now we have to train a computer to do it. So it's not enough just to be able to know what a connected component is and see physically, is that how many connected components, but being able to train a computer algorithmically to automate the process of finding connected components. That's really what we want to do. Not necessarily for connected components. We'll get to the more interesting stuff. Eventually we'll do pathfinding, even though it's not in the problem set. We'll get there. But the internet's really big, and when we have big data, and if you did watch my the lecture 10 already, the runtime lecture, that is one of the big points of that lecture is once we have a lot of data, now we have to know computer science. Like, we have to understand what's going on, or else we're going to write really slow, crappy programs. So it's all about once we have a lot of data. If you don't have a lot of data, why are you even using a computer? So this is where breadth first search comes in, or BFS. So we're going to run BFS, and what this algorithm does is explores the neighbors of nodes until it has nothing left to explore. That's the brief one-liner version of BFS. It's going to take me probably an hour to really dive into what BFS is, but that's the quick one-liner. So we'll choose a starting node. I'm going to choose UCLA here, and then we're going to repeatedly explore the neighbors of nodes that have just been explored, starting with some starting node that we explore first. So we're going to explore UCLA and then explore all the neighbors of UCLA. In this green box are all of the nodes that have been explored. And then all the 4 nodes that we just explored, we're going to explore their neighbors to get Utah and SDC here. And then we're going to explore the neighbors of Utah and SDC. And we keep repeating this process until we have a round where no new nodes were visited. So when we visited the neighbors of Utah and SDC, yeah, they see SRI and RAND, but those 2 have already been explored. So we didn't learn anything new. We didn't find any new nodes. Once that happens, BFS is done. It's done its job. And if we run BFS, choose any starting node and run BFS, and we did not visit every single node in the graph, then that graph is not connected. If it was connected, breadth first search would have found the edges that connect all of the nodes in the graph. The fact that it didn't means that it found all of the connected components of the component of the starting node, and that's it. It can't do any more than that. And I'm going to skip this slide because this is usually the cutoff of one lecture, and then I leave you with that and then come back Wednesday. But we're about to come back in a few minutes. So I don't really need the overview of BFS. We're about to do the deep dive into BFS. More details to come right now. But I do want to, right here, go through problem set 4. So I guess not right now, but go through what we're doing in problem set 4. So I'll go through each question, partly because I don't know. No, I already explained why. Because we have time in this lecture, and it's something I haven't done for the other 4. So I want to make sure we go through this one. So all these are algorithms that run on a graph. This is graphs and testing problem set. So we do have to test some of these methods. Or all. Did I put all of them? Sorry, I know I should know that off the top of my head. Yeah, we sure did. Okay. So we want to test and write these 5 methods that work on a graph. And the first one, count edges. Honestly, this one's pretty free. It's a good warm-up one just to know how to work with the graph class. Count the number of edges. Given a graph object, count the number of edges in that graph. Max degree, this is that defines a degree of a node. The degree of a node is the number of neighbors of that node. So the number of neighbors of a node is the degree. Give me the node with the max degree, or give me the degree of the node with the max degree, not the node itself. So give me the highest degree node in the graph. We do that specifically because if there's a tie, it just adds a bit of complexity that, you know what, let's skip it. If we return the value, then if there's a tie, it's still the same number being returned. Just easier for the testing. You're new to testing. We don't want to make the testing overly complex and distracting. And then the next 3 are all BFS ones. These are ones I want to talk about quite a bit more. So the next 3 all will, I hesitate to say required. You could probably come up with some unique situation, unique solution that's effectively BFS, but you're basically required to write BFS for these, to implement BFS. That's the intent anyway. There are some students who don't implement BFS, but then I look at their solution and they're basically doing BFS. They just do it a different way than what I specifically explained in class. So the first one is connected. Given a graph, tell me if it's connected or not, true or false. Is this graph connected? For this is what we just looked at with BFS. If you run BFS, choose any starting node on the graph, run BFS, and if you explored every single node in the graph, it's connected. If you didn't, it's not. So keep track of all of the nodes you've explored. If the size of your explored data structure is n, the number of nodes in the graph, then it's connected. So run BFS and then check if you've explored every single node in the graph. Next is the number of connected components. So in that last graph we saw in the slides, you should return 2. It has 2 connected components. Tell me how many connected components there are for this one. For this one, the intended solution, and for all of these, I'm going to walk through like what I would expect you to do. I'm going to pretty much tell you how to do all these questions, but I'm not showing any code. Your task is to code them up. So number of connected components, if you run BFS like we did with is connected, run BFS, choose any starting node, run BFS, and if you've explored every single node, well, your graph is connected. A connected graph has 1 connected component, return 1. If you did not explore every single node, this is where we have to do more work than is connected. If you did not explore every single node, then pick any node that has not been explored and run BFS again. Now you know you have at least 2 connected components, and then check, are there any nodes that I still haven't explored? If so, then choose one of them, run BFS again. Keep repeating this process, incrementing your number of connected components until you finally explored every single node across all of your calls to BFS. So these are explicitly meant to build on each other. You're checking, is there 1 connected component? Are there, if there's more than 1, how many are there? And if you do number of connected components first, if you're like, you know what, I'm just going for the whole shot, you can do number of connected components and then check for is connected, check, call number of connected components on the graph, and if the number is 1, it's I have to be careful here. If it's 1 or less, so if it's either 1 or 0, a graph with no nodes is connected. Empty graph has 0 components. So if it's less than or equal to 1, return true, otherwise false. So if you do number of connected components first, you get is connected for free. You don't have to write BFS twice to complete these 2 problems. You can just do this one and then use that as a helper method to do is connected. I don't really recommend that. If you're a little iffy on BFS, then the intent is that you do is connected as a warm-up and then get into a more complicated BFS question. But if you're confident, you want to just go for it, go for it. Then detect cycle. Tell me if there's a cycle in the graph. For this one, I put the hint right in the handout just to make sure nobody misses it, because this can be pretty tricky. It's hard to just arbitrarily detect cycles. There are plenty of ways to do it. Whatever way you find that you're comfortable with, go for it. Get creative. But my hint for this is that if you run... Oh, we didn't even talk about this yet. You know what? I'll give this hint in the slides. I'll give it right here briefly, but it won't make sense yet because we didn't talk about it. But run BFS. Keep track of all of the edges that you used to discover new nodes. And if that number of edges is equal to the number of edges in the original graph, then you got yourself a tree, which means a cycle was not detected. I'll explain that better in the slides. We really haven't gotten to that stuff yet. So that's the problem set, and then testing for all those 5 methods. So that's the problem set. That's what we want to be able to do. In the fall and spring semesters, we also have game feature assignments where we do full-on pathfinding with AI. So in the slides, I will still cover that content. But since we only have the problem sets in the summer, we have an abbreviated semester, you're not required to do that, but it's still, I don't know, super fun. The fact that we can do pathfinding with what we know is, I think, pretty awesome. Hopefully some of you agree. So let's do that. So that's what the slides are built for, is to build up to that pathfinding. We want to program AI that's going to hunt down the player without getting stuck on walls or stuck in corners of walls and stuff like that. We want it to be smart AI that's actually going to go around walls to the point where it could navigate an entire maze and basically build a maze solver that solves a maze, not just solves it, but solves it with the most optimal path as well, the path with the least number of edges. So we do need a few more definitions. We talked about path last time, but we can also talk about the length of a path. So the length of the path is the number of edges in that path. So this path right here, Lincoln, MIT, Utah, SDC, RAND, UCSB, SRI, 1, 2, 3, 4, 5, 6 edges. So it's either the number of edges, which you can find by the number of nodes in the path minus 1. So both are the same, however you want to code the math in your, if you're coding these things. That's the length of a path, the number of edges in that path. The distance is between two nodes is the length of a shortest path between those two nodes. So for example, Lincoln and SRI, I know that there's a path of length 3, 1, 2, 3. I'm claiming that the distance between Lincoln and SRI is 3, meaning that my claim is that there is no path of length 2, 1, or 0 between these two nodes. The shortest path you can possibly find is going to be length 3. So there are other paths to get between these two nodes. I can go this way, 1, 2, 3, 4, 5, but that's a longer path. You know, I can't beat 3. You can stare at this graph all day. You're not going to do better than 3. You're never going to do better than that. RAND and BBN are connected by an edge. Whenever two nodes are connected by an edge, their distance is going to be 1. You can't do any better than just traversing the single edge to get from one node to another. And the distance between a node and itself, if we want to go from Harvard to Harvard, the path is just Harvard. There are no edges, and the number of nodes in that path minus 1 is 0. So a distance from a node to itself is always 0. You don't have to travel any edges. You're already there. Well, you don't have to do anything. Distance 0. So let's get our second run of BFS out here. And spoilers, this isn't really a spoiler, but the third run of BFS, that's going to be our most useful one to, is that true? It's not even true. Yeah, no, that's still true. It's going to be our most useful one for our, for the code. We're building up to filling in all the details to the point where you could code this. So you have to understand the first one. Hopefully you understood that one. And then we're going to add more details on this second one, and then add even more details on the third one. So so we're building up to the big one. And the fourth one is usually the fourth one is the full-on pathfinding that we're not doing in the assignment, but it is interesting. Okay, so let's go through BFS a second time. And now, instead of just traversing the graph and exploring neighbors, neighbors of the neighbors, neighbors of the neighbors, because that sounds cool, but like, how do I code that? Instead, we're going to keep track of some extra information, and the extra information is going to be the edges that we used to explore a new node. So all the edges we took to explore new nodes, and just to be different and to emphasize the point that UCLA is not the root node, there is no root node in a graph, I'm going to start with Carnegie for this. And I'm going to keep track over here. I'm going to build a second graph that's going to only contain the edges that were used in the BFS run. So I'm going to start with Carnegie. So I'm going to put Carnegie right here. And then each time I use an edge to find a new node, I'm going to visually put it lower on this second graph and then add those new nodes. So Carnegie is going to find Case in Harvard. So I'm going to put Case in Harvard lower on this graph below Carnegie and take those edges that I used to explore those nodes. Case is going to find Lincoln. Harvard is going to find BBN. So I'm going to have Lincoln and BBN coming off of those nodes. And I have my first kind of crossroads here. I have MIT, and either Lincoln's going to get to MIT first or BBN's going to get there first. One of these nodes is going to explore MIT, and then one of them is going to say MIT has already been explored, so I'm not finding a new node, so who cares? For the slides, I get to just break this tie arbitrarily. I'm going to say Lincoln finds MIT and BBN. There's no choice. BBN has to find Rand. So Lincoln is going to find MIT. BBN is going to find Rand. And this edge right here was not used in my breadth first search run. It was not used to find a new node. And when it was checked, it found a node that was already found, already explored. So we do not use this edge. So this edge, BBN to MIT, does not show up in our second graph. And MIT is going to find Utah. Rand's going to find these three nodes. No choices to be made here. And then we have three separate nodes all fighting over SRI, and UCLA is the only one who could find Stanford. So UCLA has to have Stanford, and I gave SRI to Utah. So this edge was used. These two edges were not. Any of these edges here were not used in the run of BFS to find a new node. So I don't put them in my other graph. So I've built this second graph. I haven't explained why I built this graph, but I built it. Ain't that neat? Cool. So I built this second graph, and I do have some structure to this graph. I did draw the edges going down each time, and I only used a subset of the edges of the original graph. So I have this graph here, and this graph will be a tree. It's guaranteed to be a tree, meaning that it has no cycles. So this is a tree. It's not a tree represented with nodes and references left and right like we saw before. It's not our binary tree, but it does meet the definition of a tree, which is any node-based data structure that does not have any cycles. So this is going to be a tree, because if it's the edges that we skipped, if we added in any of the edges that we skipped, we would end up having a cycle. So we have a tree here. And in fact, every tree is a graph. It has that same relationship with every square is a rectangle, same thing. A tree has all of the, meets all of the definitions of a graph. It has nodes connected by edges. It is a graph. The binary trees we talked about earlier are still considered graphs as well. They would be directional graphs. We can't go from a child up to the parent node, but they would still be considered graphs conceptually. We represent them as binary trees in our code with binary tree node, but conceptually, every tree is a graph. So we have a tree here, and it has levels. So the way we drew this, where we're drawing it kind of like our binary trees, except it's not binary because we have this node with 3 child nodes. So we have our tree, and if the way we drew our nodes going lower on the slide each time, we can separate these into levels and say we start at level 0, and every time we go down with an edge, we're going to increment the level by 1. So we have 6 different levels in this tree, and the level number, if we do this, set up our tree this way, the level number is exactly the distance from the starting node to that node. So all the nodes on level 2 we know have distance 2 from Carnegie. On level 4, all these nodes have distance 4 from Carnegie, meaning that from Carnegie to any of these nodes, the length of the shortest path from Carnegie to these nodes has to be 4. You cannot get from Carnegie to any of these 4 nodes with 3 edges. It cannot happen. If it could happen, BFS is guaranteed to have found those shorter paths, the shortest paths. So not only do we have the distance from the starting node to any node in the graph, but we actually have a shortest path from the starting node to each node just by traversing the edges in this tree. So to get from Carnegie to MIT, we have a path going from Case, Lincoln, MIT. And remember when we skipped an edge, Lincoln and BBN were fighting over MIT. If we change this and got rid of this edge and instead used the BBN, we go Carnegie, Harvard, BBN, MIT. That's fine, but MIT is still distance 3 from Carnegie. Both those paths are length 3. And in fact, whenever you ignore an edge when you're running BFS, that edge would find, whenever you have an arbitrary decision like that, what edge to choose, whatever edge you choose, the distance will still be the same. What that means is there are multiple shortest paths from the starting node to that node, and it doesn't really matter which one you choose depending on your specific application. But if you're trying to find a shortest path or the distance between the nodes, it doesn't matter which one you pick, you're still going to find a shortest path. This is, I know there's one more thing I want to say about this. This tree, so this is my hint for that last question, the detect cycle in the problem set. You can do something with, whenever you find an edge to a node and that node's already explored, you can do that, but there are tricks to that. If you want to go down that path, I'll let you explore it. But my hint for this one is to run BFS, choose a starting node, run BFS. If the graph was not connected, continuously run BFS just like you will do in finding the number of connected components. Make sure you run BFS on every connected component of the graph. And build the BFS, what we call BFS tree, like we just did. Build this tree, so create a second graph and add in every edge that was used to explore a new node. Add that to your second graph that's going to be your BFS tree, or technically a BFS forest if the graph isn't connected. Yes, we do get cute like that, where if there are multiple trees in a graph, in a disconnected graph, we'd call that a forest. Because why not? Multiple trees, it's a forest. And build this BFS tree or forest. And if that I'll say tree because I don't feel weird saying forest. If that BFS tree, take that BFS tree, count the number of edges in it, which your first method is count edges. Call count edges, check the number of edges in that tree, and then call count edges on the original graph. If those two numbers are the same, then you didn't have any cycles. Because if you have any cycles in your original graph, when you build a tree, the cycles need to be removed. So if you never had to remove any edges, that means you didn't have any cycles, and your original graph was a tree because it had no cycles. So if you didn't skip any edges, then you didn't have any cycles. You had yourself a tree, and you can return, nope, no cycles detected. But if the number of edges in the tree is less than the original number of edges in the graph, that means you did skip some edges that would have introduced cycles. That means there is a cycle in the original graph. So that's my hint. That's my hint for you to be able to detect cycles. Yeah, like I said, there are other ways. Feel free to explore other ways. But I think that one's pretty simple. I think that's a pretty simple way of solving the question. If you disagree, do something else. That's fine. As long as you solve the problem. As long as you solve the problem. Emphasis on you. You have to solve it. Don't just look it up online and steal somebody else's answer or use an LLM. Obviously, that's cheating. But as long as you solve the problem, solve it any way you want. Okay. So let's get to our third run of BFS. I advertise this as the most important one. Let's do it. So with this one, what the context of this is going to be finding the distance between any two nodes. That's what we'll find here. The problem set, we're not interested in distance itself, but this is still going to explain the structure of how to be able to set up BFS, and then you'll have to do it to detect cycles, count connected components. But this will show you how to set it up in your code, because so far we said draw the tree visually on the slide and have the nodes visually go lower on the slide. Like, how do you code that? Like, it doesn't really make sense how to code that yet. So let's talk about how to actually code this thing. Again, in the context of finding the distance from the starting node to any node in the graph, but the whole setup, the whole structure is what's going to be helpful, even when we're not interested in distances. You do these as, I don't know, Booleans instead of distance and track different information. But this is how we want to roll with it. Actually, we could probably just get rid of this entirely. You may not need that, but you'll need the rest of it. Anyway, that's for you to figure out for your problem sets, the minimum you would have to do. And we're going to do this with 3 different data structures. So the oh, my brain stopped for a second. So this is another reason why I really like graphs as a capstone for data structures in the course, is that we're going to use 3 different data structures, and ooh baby, one of them is going to be a queue. We finally get an application of queues. We never really get an application of stacks, except the memory stack, so we kind of do get practice with that. But we finally get a queue in here. Makes me excited, I don't know. So we have 3 different data structures. Let's go through them. We have a queue. This is going to keep track of the nodes that need to be visited in a very specific order, in this first in, first out order. Having this be a queue is going to be critical to checking the nodes in the right order. Kind of. I mean, for distance, it's critical. For the problem set, actually, you could use a different data structure here. If you use the stack instead of a queue, I'm pretty sure you'd still get what you want for connected components and detecting cycles. Yeah, you should. Yeah, you would. For finding distances, critical that this is specifically a queue, and yeah, that's all I want to say about the queue until we get into the runtime of the algorithm. And then this might be the most important data structure for the problem set, is some data structure that's going to keep track of which nodes have been explored. In the slide, I'm going to mark them in orange to indicate that they have been explored. In your code, you're going to have some data structure to be able to keep track of this. The correct data structure is a hash set for this. In that'll give you O of 1 operations. But you're free to use whatever data structure you want here, because I've never talked about sets or hash sets in 116. Can't really expect you to do that. Plus, we don't really care about runtime in 116. We talk about it a bit, but in your Autolab submissions, if you don't have the optimal runtime, just not concerned. That's what CSE116 is for. They'll do all that stuff. So if you want to use an array list for this, array list has .contains, which is the big question we have to ask this data structure. Has this node already been explored? If you do that with an array list, that's fine. If you want to use a hash set, just use a hash set. It also has .contains. The syntax is the same. It has add and contains. So you can use that. One difference with a set is just like if you did take 191 or any math class that talks about sets, it does have the property you would expect from a set from any math class, is that it cannot have duplicates. So if you add a duplicate into a set, it ignores that and says, hey, we already got that one. We already have one of those. We don't need another one. So if you want to use hash set, it's really the same thing as using an array list. It has add and contains, and those are the 2 methods we're concerned about. We want to mark a node as explored. There's going to be adding into this data structure. And we want to ask the data structure, has this node already been explored, which is going to be .contains. Does this data structure contain this value? And our third one is going to keep track of the distances from the starting node to any node in the graph. So for every single node, what's the distance from the starting node to that node? That's what BFS tells us. If we want the distance between any two nodes, we choose one of those nodes to be our starting node, and then the other node is our ending node. We don't have to end, but the other node we're going to look up after we run it and check. If we want to find from Carnegie to SRI what's the distance, we would choose Carnegie as our starting node, run BFS, and then at the end of BFS, we'll ask this data structure, hey, SRI, what's your distance from Carnegie? And the slides, I'm initializing all these values to infinity. I'm doing this just because I think it looks better on the slide to have this data structure entirely here. In your code and in my solutions, in fact, I don't do that. I will add one key value pair at a time into this data structure. So if a node is not in this data structure, that means it hasn't been explored yet, which I've seen some students do this. You can use this, the key set of this. This will be a hash map, by the way. I don't think I mentioned that. The map right here. This key set, if you do it that way, would be the nodes that have already been explored. So you can ask this data structure dot contains key to figure out if a node has been explored or not. Whoa. So we set up these three data structures: a queue, some data structure, preferably a hash set, but I won't be mad at all if you use array list. I would really expect array list for this one, and then a hash map to keep track of the distances. And we're going to initialize all three data structures with the starting node. So we're going to enqueue the starting node, mark the starting node as explored, and set the distance of the starting node, which distance from a node to itself is always 0, so initialize that to 0. And then we're ready to run BFS. We're ready to run BFS with the details of how to actually code this up. We got our three data structures, and the way BFS is going to run, I can explain it in one sentence. We're going to go through the entire run of BFS. It's going to be, towards the end at least, somewhat excruciating, somewhat tedious, but we will go through every single detail. But BFS in one line is, while the queue is not empty, dequeue, explore the neighbors of that node that have not been explored, and every time you explore a node, enqueue it, mark it as explored, and set its distance equal to the distance of the node that discovered it plus 1. So case will get 1 here. That's BFS. That's the whole thing. That's like all of the code. If you code up those English sentences as Java code, you have BFS. Like, it's done. And you can at least do the is connected with just what I said right there. But let's crack that open and talk about what that actually means, because there's quite a bit going on there. So with BFS, we're going to dequeue from the queue. We're going to run BFS while the queue is not empty, which I don't really even have a better way of saying it. If that sounds like a while loop, you should have a while loop. You can use the queue that we wrote in class. If you use that one, you might want to add an isEmpty method to be able to tell, just return is front null. That's the question, and that'll tell you if it's empty or not. Or you can use Java's built-in queue class. Java does have a built-in queue class. You can import that from Java util, and it does have an isEmpty method already built in. So you have a few choices there. Or you can just use a linked list and use it as a queue and check if it's null. If it's null, it's empty. But whatever you do, you want to go, while this queue is not empty, you're going to run your BFS loop. That BFS loop is dequeue. So we're going to dequeue Carnegie, and we're going to explore any neighbor that has not been explored. So we're going to go to the adjacency list and say, hey, adjacency list, give me all the neighbors of Carnegie. And then for each neighbor, we're going to have another loop here. For each neighbor, we're going to check, has this node been explored already? For this case, the answer will be no. Case has not been explored, so we're going to explore it. To explore a node, we're going to enqueue it, mark it as explored, which I'm using orange for here, but you would add to your array list, and then mark its distance as the distance of the node that discovered it, which is 0 in this case, plus 1. So the distance from the starting node to Case is going to be 1. And same thing for Harvard. We're iterating over the neighbors. We check Case, we check Harvard. Harvard has not been explored, so enqueue it, explore it. Distance equal to the distance of the node that discovered it, plus 1. And then we repeat forever. We just repeat until not forever, but until the queue is empty. So Case is at the front of the queue, so the next step is to dequeue Case. That will be at the end of our loop. We already checked all the neighbors of Carnegie. Get back to the front top of our loop. The queue is not empty, so we're going to go through the loop again. We're going to dequeue. We're going to look at all the neighbors of Case. So we're going to look at Lincoln. We're going to see that Lincoln has not been explored, so we're going to enqueue it, mark it as explored, set its distance equal to Case's distance plus 1. So we're going to set Lincoln's distance equal to 2. Then we're going to check Carnegie, because in the array list, we're just going to get every single neighbor of the node. And this is where it's very important we don't go infinite here. We're going to check Carnegie, and we're going to ask this data structure, this array list, we're going to say, do you contain Carnegie? Has Carnegie already been explored? And in this case, the answer is going to be yes. Carnegie's already been explored. So we don't do anything. If a neighbor's already been explored, we completely skip it. We certainly don't want to enqueue it or do anything like that, because then we're going to go infinite. This is the difference between a graph algorithm and a tree algorithm, is we're checking, hey, have we already processed this node? If we've already processed it, we need to not process it again, or we're going to go infinite as soon as we hit a cycle, or even the worst case, not even a cycle, but an edge connecting two nodes, and just keep going back and forth on that edge forever. We want to make sure we avoid anything like that. Don't want to do that. So now Harvard is the front of the queue. We just did all the neighbors of Case. Harvard's the front of the queue. DQ, check the neighbors. Carnegie already explored, so we don't do anything. BBN has not been explored, so we enqueue it, mark it as explored, set its distance equal to Harvard's distance plus 1. And now we're at the situation in our previous run where we had an arbitrary tie and we had to choose one of these nodes to be the one that discovers MIT. The way it works when you actually write the code is there won't be any choice to make. You won't have to add any extra code to be able to handle this situation. And we can see exactly how this will play out now. We're going to dequeue Lincoln. We're going to check the neighbors of Lincoln. MIT has not been explored, so we enqueue MIT, mark it as explored, set its distance equal to 3, Lincoln's distance plus 1. Then we're going to check Case. Case has already been explored, so we don't do anything. Then BBN is the front of the queue, so we're going to dequeue BBN. We're going to check all of its neighbors. We're going to find Rand, enqueue it, explore it, set Rand's distance equal to 3. Check Harvard. Harvard's been explored, so we don't do anything. And we check MIT, and MIT's already been explored, so we don't do anything. It doesn't matter that it was like just explored just by Lincoln in the previous node. It doesn't matter. It's already been explored, so we don't do anything. We process Rand, Harvard, and MIT, we skip them. We just don't bother. And the way this works, the way that tie was arbitrarily broken, because we're interested in distance here. Distance, if we go this way, 1, 2, 3, is distance 3. If we go this way, 1, 2, 3, distance 3. So that's how we came up with this arbitrary decision, because the distance will be the same no matter what. If it's always going to be 3 hops from Carnegie to MIT, doesn't matter which way we take. The tie was actually broken by the very first thing I did in this run, is when I enqueued Case and Harvard, I enqueued Case before Harvard, which means Case got dequeued first, which means Lincoln got enqueued before BBN, and then Lincoln got dequeued first and found MIT. So it actually depended on the order in which I added the edges in the adjacency list when I first created this graph. So if I add Carnegie Case before Carnegie Harvard, then MIT is going to be found by Lincoln instead of BBN. So it has a kind of cascading effect. But it's a choice you don't have to make. It just matters on how you built the graph, and the results are going to be the same, especially for connected components. It's not going to matter at all in detecting cycles. So, but that's how that works out in the code. Just how we build the adjacency list is going to determine how those ties are broken. No extra code. You don't have to say, oh shit, we have a tie, and then write some code to be able to tell how to break ties. It just comes out in the wash. You don't have to think about it at all. And MIT is going to have distance 3 no matter what. And we can start seeing the pattern of why that is at this point. So we started at Carnegie in the queue, which was every node of distance 0. And then when Carnegie explores nodes, the only way to get a distance 1 node is to be a neighbor of Carnegie. So we enqueue all of the nodes of distance 1. Then when those nodes of distance 1, they're going to be dequeued one at a time and start enqueuing all the nodes of distance 2. But we're going to process all the nodes of distance 1 and dequeue all of the nodes of distance 1 while enqueuing all of the nodes of distance 2 before we move on to anything else. Then we're going to have all of the nodes of distance 2 being processed, Lincoln and BBN, which will add all the nodes, enqueue all the nodes of distance 3. So MIT and RAND are the only 2 nodes of distance 3, and they're going to start adding, enqueuing nodes of distance 4. So because we're using a queue specifically, we will process the nodes. We will end up dequeuing the nodes exactly in distance order. And that's how we get nice properties out of BFS. This is how we can calculate distance in our nodes. So how do we know MIT, we gave it distance 3. How do we know for sure it's distance 3? Well, because when it was explored by a node of distance 2. And if we're guaranteed to be dequeuing nodes in distance order, the fact that we're dequeuing a node of distance 2 means we've already processed all of the nodes of distance 1 and 0. And while processing the nodes of distance 1 and 0, we did not explore MIT. That means MIT is not connected by an edge to any node of distance 0 or distance 1. So the best it can do is be connected to a node of distance 2 and have a distance of 3. So if it had distance less than 3, we would have already discovered MIT when we dequeued the nodes of distance 0 and distance 1. So that's my kind of quick hand-wavy proof of why we're actually getting the correct distance numbers from BFS. It's a very nice property. I believe probably not until 331 you'll go through the actual formal proof of why we get this information out of BFS. I think they do. They used to. I don't know if they still do. I don't think they moved that to 250. But you should see that at some point in your career, if you're assuming you're computer science and not computer engineering or something else, where you skip 331. So now we're going to dequeue these nodes of distance 3 and find the nodes of distance 4. MIT is going to find Utah of distance 4. And we're adding 1, by the way, to account for that next edge. Lincoln, we know, has a distance to Carnegie of distance 2, so we know there is a shortest path from Carnegie to Lincoln of distance 2. If Lincoln discovers MIT via an edge, we know whatever that path that we took of distance 2 from Carnegie to Lincoln, we can take that path plus 1 more edge to get to MIT. So MIT's distance must be Lincoln's distance plus 1. RAND is going to explore 3 different nodes. When it checks BBN, it's already explored, don't do anything. And then Utah is going to find SRI. SDC and MIT are already explored, so don't do anything. SRI came from Utah, which is distance 4, so SRI has distance 5. UCLA is going to find Stanford and then skip these other 3 nodes. They're all explored, don't do anything with them. Stanford gets a distance of 5. And at this point, we can already tell visually, on the slide at least, that we're done. We've explored every single node. And notice that we never update a distance number. Once we have the distance of a node, that's it. That's the final answer. That's the distance from Carnegie to that node. End of story. So we never update these values. We already explored every node. There's nothing left to do. But in our code, you can add a separate line that says if we've explored every node, just get on out of there with a break statement. But it's perfectly fine to let it run out through its natural course and dequeue the rest of these nodes. Dequeue UCSB, it's going to check all its neighbors, see that they're all explored, and not actually end up doing anything. SDC, check all its neighbors, they're all explored, don't do anything. SRI, don't do anything 4 times. Stanford, don't do anything, don't do anything. And then finally the queue is empty. That's going to break us out of our loop and say, hey, we've explored the connected component of the starting node, so there's nothing left for us to do. The queue's empty, and we have all of our distance values. So we have all the distances from Carnegie to every other node. Same information we got with the level example, except now we actually know how to code this thing. I talked through what data structures to use and what loops to use. Pretty much walk you through exactly how to do it to be able to code up breadth first search that can find distance from the starting node to any node in the graph. And if there are any questions on that, if you understand the runtime of that, how to build, that in the code, you're doing awesome on that problem set. You probably ran off to go do it right now, finishing it so you can be done with this course. Because this is what you need to know. The explored nodes here, you know what nodes were explored. So when you're finding connected components, the number of connected components or detecting cycles where you might have a disconnected graph, check your data structure that has all the explored nodes, check its size. If that size is less than the number of nodes in your adjacency list, which you can ask the key set for its size, then you got more work to do. You got to find a new node in the graph that has not been explored. Choose that as your starting node and run BFS again. So you'll end up running BFS in a loop that's going to continuously grab a new unexplored node until every single node has been explored. So if you have questions with that, I want to know them. If you don't have any questions on that, you are golden to just crush and cruise through problem set 4 and finish this course. Unless you have to take the final, but I don't know if it's a false assumption or not, but I assume at least most students most of you who are actually hearing me live probably don't need to take the final. I suspect there's a high correlation there. On YouTube, I have no way of really knowing who's here and who's not. But I would suspect that y'all don't need the final. Finish up problem set 4, be done with this course. You'll be done with this course today. And then not have to think about 116 ever again. So I'll keep watching for questions, but let's cruise on to the next example. So I did promise pathfinding. So how would we take this and do pathfinding? Because knowing the distance between two nodes isn't that not that interesting to us when we're trying to do full-on pathfinding. But we can make one small adjustment to what we did here and do our full-on pathfinding. So instead of checking the distance from the starting node to each node, I'm going to tweak this a little bit and instead store the node that was used to explore that node. Which node found each node? And then for the starting node, we need some special marker. I like null is perfectly fine in the code. And something to be able to mark that as the starting node. Say, nobody explored me. I am the beginning of everything. Everything started with me. And then each time we explore a node, keep track of which node discovered it. So Carnegie found Case and Harvard. So Case and Harvard, the first time they were explored by Carnegie. So we're going to mark them as being explored by Carnegie. So instead of distance, we're tracking just the node that found that node, that discovered that node. Lincoln and BBN. Lincoln was found by Case. BBN was found by Harvard. MIT we gave to Lincoln. So MIT was found by Lincoln. Rand was found by BBN. And I won't go through every single step like I did with the last one. Hopefully you see the pattern there. Every single node, whenever we find it with an edge that we marked in yellow here, SRI was found by Utah. We're going to mark that in this data structure and say SRI was found by Utah. So every single node knows the node that discovered it. And that's it. And that's all the information we need. We can actually do distance with this information quite easily as well. So to find a path, a shortest path, BFS will guarantee, we find where we're headed to and work backwards. So let's say we want to find the shortest path from Carnegie to Stanford. What we're going to do is start with Stanford and then build backwards based on that. And we're going to keep asking this data structure question. We're going to say, Stanford, who discovered you? Where'd you come from? And Stanford's going to say UCLA. So we build this backwards. And we used to do this with a linked list to get another data structure in here and prepend to a linked list since we know that's nice and fast. So Stanford has to be our last node. That's our destination. And we're going to say Stanford, who found you? UCLA, prepend UCLA. UCLA, who found you? Rand, prepend Rand. Rand, who found you? BBN, prepend BBN. BBN, who found you? Harvard, prepend Harvard. Harvard, who found you? Carnegie, prepend Carnegie. Carnegie, who found you? No one found me. I'm the start node. No one can find me. I found myself. So once we find this indicator that says this is the starting node, that means we are done. That's our path. So a shortest path, which is the shortest path in this case, from Carnegie to Stanford, here it is right here, with using BFS and a quick change to our distance calculation, tracking the node that found each node, we have that shortest path in our code. And if we want to use this to find distance, you find the shortest path first. You only have to run BFS once. Find the shortest path first, and then find the distance of this path. We have 1, 2, 3, 4, 5 edges. So we have a distance 5 from Carnegie to Stanford. So we still get the distance information. We have to do one extra step to find the distance. But if we want to do full path finding, this is how we can do it. So we can find a shortest path. Like for Carnegie to MIT, we find a shortest path. It's not the shortest path, so I try to be careful with my words there. Carnegie to Stanford, we did find the shortest path. There is no other shortest path. We know that, well, we can stare at the graph and 1, 2, 3, 4, 5, 6, like every path is going to be longer. But we also know that because when we found Stanford, we found it through nodes where we never made a choice. Like BBN, Harvard was the only node that could find BBN. BBN was the only node that could find Rand. Rand was the only node that could find UCLA. UCLA was the only node that could have found Stanford. For any of those nodes, we didn't make any choices. There were no arbitrary ties or anything. No one ever... no, that's not true. I was going to say no one ever looked at these nodes and said, no, that's already explored, but that's not true. Like just going backwards. Anyway, we didn't make any choice. So this is actually the shortest path, which is frickin' cool. But for the fall and spring semesters, we do have the students do a whole game engine, which you can find if you are interested. You could find these assignments, by the way. If you go to the course website repo and roll back to the spring 2026 tag, you could actually pull up that version of the website, get the handout, go to the repo, clone the repo, get the code. If you are interested in this, you can still do it. Just because you're not forced to do it in the summer doesn't mean you're missing out. You can absolutely still just do it anyway. Nothing stopping you from that. But this is what we'd have them do is say we have this AI character here and this one here. We want to be able to find the shortest path, from this enemy to the player without getting stuck on walls. If you do a naive coding, naive implementation, this character is going to go straight for the player and get stuck on this wall right here where they can't actually reach the player. and that's not a very fun game. When you have a game with really dumb AI like that, it's not really that interesting. Uh, but uh, but with BFS, we can get this AI to track down the player while avoiding walls. So what we do is build a graph out of the level. So this is a tile-based game. You can be between tiles, but we find the closest tile for each character and then use that as their location. So for each tile has a node, and then every tile is connected to any adjacent node that can be traversed. So we say these solid objects here can't be traversed, and walls, of course, can't be traversed. So we don't give them nodes, or we give them nodes and just don't connect them to any other nodes because it's not a valid movement option. So these are all of the valid moves that an AI can take. If they're right here, they can move left, right, or down. Say they move down, now they can move left, right, up, down, but they can't move into a wall. They don't have that option, so we don't give them that edge because it's not a valid option for them to take. So we build a graph out of the level of all the possible moves that can be made between two tiles. Then we program our AI using this graph. So when you're playing the game, you see the actual visuals and stuff, but the AI is only looking at this graph and doing computations on this graph. And the AI is going to mark two locations, their location and the player location. That's the start and end of their path. And then they're going to run BFS on this graph. So they use themselves as the starting node. They use the player as their ending node. Well, they use their self as the starting node, run BFS. For every single node, they remember which node explored them. And then they work backwards from the player's location. And they say, player's location, which node found you? This node, which node found you? Etc. And get all the way back to the start with a shortest path. There are a lot of shortest paths for this one. The player, if the AI went this way to the right and then down, instead of down and then to the right, that's the same distance. That's perfectly fine. It could go down, down, right. And over here, it could go left right away instead of going up and then left. A lot of different shortest paths. But it will find a shortest path. And then the AI traverses this path, gets to the player. Depending on what features you want on the game, you can have them update their path every frame. So as the player's moving, they'll keep hunting down the player. For what it's worth on the assignment, we had them traverse this entire path. So they would go to the old player's location and then recalculate and hunt down the player again. Depends what features you want on your game. We didn't want too smart of AI, or else then it's just hard to play. Okay, so that's how we can. Excuse me. That's how we can have smart AI pathfinding in a game. And this is powerful enough, like I said at the beginning, this is powerful enough where if the level is a legit maze, it will still traverse that maze. Like there's no real limit to the complexity of the level. Like these AI just are not going to get stuck on walls. Not going to happen. All right. If there are any questions on any of that, that's really the content I want to show. I'm going to do some live coding, but actually, let's take a little detour. Let's have a little fun at jessehartloff.com. This is, we're on level 1. Let's try to beat level 1 real quick. This is an old assignment. Students would actually build some of the features of this game. I'd give them like the skeleton and they'd build it out. Let's see if I can dodge these towers and take this down. If you go to jessehartloff.com, you can actually play this. It's it is an MMO. I was gonna say technically an MMO, but no, it just is an MMO. Here we go. And what this is doing, so these blue dots are helper players. They are ran with AI. So each one of those players is starting, they spawn at the green square, and they use BFS to find the shortest path to the target, which is the yellow square. That's the base we're attacking. So they will use BFS. They do use BFS to calculate that path and go right to it. This is level 1, so it is just a straight path. Not super interesting, but once we get to level 2, we will see them actually traverse around walls and take a shortest path to the goal. And we're getting there. Might as well explain other things while we're here. These towers, I kind of have to stutter step for these towers. These towers do aim where you're going to be. They'll actually check where you're going to be and lead the player a little bit. So they are a little tricky to dodge. If I just hold right, I'm going to get hit by the towers. Like, pretty well guaranteed. Like, there I just held right, I'm going to get hit by that tower. So I do got to, once they fire, do a stutter step to make sure that I dodge that bullet. And they're actually doing that using a genetic algorithm. So they're not coded to lead the player. They don't do any geometry or anything or anything like that. They actually use a genetic algorithm to basically guess and check where to aim for that player. So they run a genetic algorithm every time they fire to be able to hit that player, and then optimizing the genetic algorithm so it's nice and performant was one of the challenges that students had to code once upon a time. 116 used to be fun. I shouldn't say it like that. 116 still fun. But 116, we used to have y'all do a lot more than what we ask you to do now. I hate to say it, but it is kind of watered down now. We went from functional programming with genetic algorithms and concurrency to a couple data structures and OOP. It's kind of sad. But here we can actually see the AI characters avoiding these walls. They will go around the walls and navigate to that square without just getting stuck on the wall. A naive AI would probably go up, get stuck on this wall right here, and then never move again. But we have these AIs running breadth first search, so they're going to avoid all these walls. Oh. And the level gets a bit tougher. Let's lock in and do this. Oh man. I use these AI's meat shields. Oh, right at the end. Okay, I'm getting one hit on this tower at least. Saw that coming too. Oh, come on. I got a few AI in there though. Alright. I want to get to graph live coding, so I might give up on this. Hey, never mind. Right before I gave up. Okay. Went through problem set 4, did all that. Let's do some live coding. So I want to do, just to make sure that we are on the same page, I am actually going to spoil, oh, I gotta open it back up, spoil count edges. So let's do count edges. So this we want to write, and I just did PS4, I'm not going to do it with all the structure and everything. But count edges, whenever I have a method name like this, something that needs to be named exactly, I'm always going to cut and paste. So I need a method, and I'll look at things carefully. It should say static in here. You will complete public static methods. So I know this is going to be public static. The method name is count edges. It takes a graph as a parameter and returns an int. And the graph, I'm like, did I forget to mention this? No, I mentioned up here. Each method takes a graph of t. So these are arbitrary graphs. We don't know what the type is. It can just take any graph at all. So I have a graph of t graph. And returns an int. I want to parse it the way you would be expected to parse. And then in the handout, I do give all the signatures, but this is where you would add your type parameter list. It is true, right? I better. Go to the handout, problem set 4. Yeah, all the signatures are there. Because of this type parameter list, I didn't want anybody getting hung up on that. So you get all the structure of it. So count edges we have in the proper structure here. And we want to return the number of edges in the graph. So for this, graph has a... Let me change this. Actually, let me replace it entirely just to show exactly what you would be working with on the problem set. Let me go. I suppose I could have just cloned the problem set at this point. But data structures, graph, raw, and copy. This is the graph class that you'll be using on the problem set. I don't get autocomplete on that one, I guess. And we're gonna have a bunch of errors somewhere. Movie graph, generate graph. That's not. That's not an error though. Why does it complain about that? 4 related. They were all related to my PS4, I guess. So this is what we're working with on the problem set. And by the way, you can add methods to this graph class. You don't have to stick with just what's there. Just don't call your extra methods in your tests, because when your tests are ran against the other solutions in Autolab, we won't have any methods that you made up. So you would get errors in that. But you can add to this class if you'd like. So add bidirectional edge, that's the big one we'll use to create our edges. Add node, just in case we want a node that's disconnected from the rest of the graph, which you'll want for test cases to find like connected components where one of the components is a single node. That's a good edge case to test for. So you want add node for that one. And then get adjacency list that we didn't see in the slides. It is just a getter for, oh man, I don't have my this dot in the handout. We will use this just to get the adjacency list. It is just a getter, but we do need access to that adjacency list, or else, you know, it's tougher to work with. And then a toString can be helpful for debugging. So if we want to count the edges in this graph, the first thing we want is the adjacency list, which is going to be a hash map of t to array list of t, adjacency list. I can't spell array apparently, and since I spelled it wrong, I didn't get the auto import. Oh, and I didn't get the auto import on hash map. So that gives me my adjacency list. If I want to count the edges, an adjacency list has the keys are nodes and the values are the neighbors of all of those nodes. So if I want to get the number of edges in this graph, I can iterate over all of these array lists, all of the neighbor lists, array list of t neighbors in adjacency list dot values, and then count them. Int, I'll just call this count. And then count plus equals neighbors dot size. So I'm counting up all of the values in the adjacency list. How many neighbors does every single node have in this adjacency list? Which is almost going to give me the number of edges. The problem with this is that every edge is in the adjacency list exactly twice. So we'll divide it by 2. This will be integer division. Count and 2 are both ints. But I know that my number of my sum here of counting up all the neighbors of all the nodes, since it's a bidirectional graph, I know that that will be an even number. It has to be. It's exactly the number of edges times 2. So I'm going to divide out the 2, not worry about integer division because I have that accounted for logically. So we're going to divide that by 2 and return that. And that's the number of edges in our graph. I'm only spoiling one question. I just wanted to give some example usage of a graph there. But I'll call this method to make sure it's very clear that we're not doing anything here. Make it return void. But there is, I might be blanking on the exact syntax. We'll learn together. We'll figure this one out. But there is a situation where you need to pick a node. I've said that many times throughout the lecture, like pick a node as the starting node. If you're finding the connected component, you pick a node as the starting node, run breadth first search, and then if you did not explore every single node, then choose a new node that has not been explored, and then run breadth first search again. So a lot of times you're choosing a node. So how do we choose a node from a graph? Well, we can go, like if we're just choosing the start node. So we can go to the graph, we can get the adjacency list. Let's actually do that this way. We can get the adjacency list. That's the only thing we can ask of the graph. And there are a few ways to do it without any help. Probably what I would expect you, without any hints, I should say. Without any hints, I would probably expect something like this. Nodes equals new array list, adjacency list dot key set. Does this even work? Yeah. I don't know if set extended list. Wait, does it? Hold on, I have to investigate here. Key set, new key set extends abstract set. Implement set, extends abstract collection, which is a collection. Then array list. I thought this took, it does take a collection. Okay. It doesn't take an array, so an array is not a collection in Java. That's I guess good to know. An array is not a collection. Because you can't just stuff an array in here, you have to call arrays.asList. I thought this constructor took a list, but I guess it goes all the way up to collection, which is which is higher up in the inheritance chain. So there are more data structures that are collections than are list. And keyset is a collection, and we don't need specifically a list, even though we use arrays.asList earlier in the semester. So now you have the nodes, and then you can say if nodes.size equals 0, return. Make sure that the size isn't 0, and then your t start node equals nodes.get of 0. This is what I expect you to come up with if you're like, how do I just get a node out of this thing? Stuff it into an array list and then work with that. If you want to get the first node without doing that, there is a way to do it. Start node 2. We're going to go to the adjacency list. I'm blanking on the exact syntax, but we'll figure it out. And get the iterator. Get the key set. Get the key set and get an iterator. And then get the next value out of that iterator. So an iterator is going to let us iterate over the values, which is usually used in our for each loops. If you write a for each loop like I did right here, what this is actually doing is getting the values data structure, getting its iterator, and then repeatedly calling next on it to get the next value in that data structure. So we can still use an iterator without a for each loop. We're going to get the iterator and ask it for its next value, and we would still have to check if there are any nodes at all. If there are no nodes and you ask an iterator for its next, it's going to return null, and then you'll probably end up with a null pointer exception depending on what you do next in your code. Right? Well, that's why I'm getting an error. I have too few braces. So this is the way if you want to do it in one line without messing with all this stuff. I mean, this might be somewhere else where you do your check. That's kind of your preference. If you want to do this to just grab a node, it doesn't matter which one, so you can just grab the first one. Or if you want to do this to grab a node, either way is going to work fine for you. So this is a little more verbose, but it uses only things that we've seen in class. We could actually get this into one line if you want to do it that way. So there's two different ways that you can get a node out of the list. Let's do this way. You can check if the adjacency list is empty. The adjacency list is empty. You have an empty graph. You'll have some bullet point for each question that says, you have a bullet point that says, if the graph is empty, this is what you should do. An empty graph has no cycles. An empty graph is connected. An empty graph has 0 connected components. So that's what we should do in all those. Of course, it would have 0 edges, but that's already covered here. The adjacency list itself will not be null. Values will be empty. This will never do anything. You have 0 divided by 2. That's perfectly fine. And then max degree would do the same thing. You wouldn't iterate over anything. So whatever your initial max is, which really should be 0, you would just return 0. So here's two different ways to get just a node out of an adjacency list. That's something just doesn't come up naturally throughout the entire course, how to get a random key out of a map. So there's a couple ways to do it. And I want to do movie graph. I don't know how, like, it's a neat example. It gives us more experience with graphs for sure. But admittedly, it's not super useful for your problem set. So I'd rather take a request. If somebody has something they want to see, something you're confused about, I'd rather do that. I usually do the movie graph example because it's helpful for the game features, doing the pathfinding with the AI. It does help with that, which is why it's part of the lecture content. But if you're only doing the problem set, I don't know. I feel like there's something better we can do. Maybe I'll just glance at the problem set and see what we can do over here. Maybe testing. Actually, we didn't do any testing with graphs. Sort of test for count edges. I guess if I spoiled the code for count edges, might as well spoil some more with count edges. New Java class, test, count edges. And we can verify that I did it right. Test. And the way I type test there, that happens fast, so I can slow down a little bit. The way I'm doing test, it gives me this list of what I want, and since I'm just hitting enter here on test org.junit, it's going to do my import for me as well. So I have org, import org junit test. That just automatically gets there for me. And then public void test count edges. Assert true. And then the option it gives me is to import that statically. So that's how I get my static import. Or just to prove the point that autocomplete is only going to be, I think this came up in the async lecture actually, but autocomplete is only fine, especially in the context of this course, but even out there in general, I think this would be, it's a good rule to follow. Autocomplete is only fine if it is typing what you would have typed, or at the very least, types something that you completely understand. Then it can be fine. But once you have autocomplete writing code that you don't even understand, you're asking for trouble. And that sentiment is becoming ever more relevant these days as people are just generating AI slop as their code. Making sure you understand what your code does is going to prevent lots of issues where if the AI slop doesn't do what you want it to do and you release it to the public, how do you fix it? Like, what do you do after that? AI, fix it for me. Well, it failed the first time. Maybe it'll do it right this time. But I'm going to import static org.junit.assert true. So that's going to give me my, I'm going to fail this test, false. That gives me my assert true, but I'm actually going to want different asserts. So I'm going to do star right here. That's my wildcard to import all of the methods in the assert class. I think I cracked this open in the other lecture when we first did this, but we can see these static methods, static assert true, with either just a conditional or a conditional and that optional hint string as well. If you call the one without a hint string, it gives you null for the hint string. And then checks for null eventually will, in fail, will check. If the message is null, just that's it. But if the message is not null, display that message to the user. So to test, we're going to need a graph, and we get to pick the type parameter. I like to just do integers because it's, I don't know, it's just the easiest thing to do. My graph equals new graph, and we want to add some edges to this graph. Graph dot add bidirectional edge. I want 1 to 2. 1 to 3, 1 to 6, 6 to 4, 12 to negative 13, and 20 to negative 13. Sure. And then I expect, I added 1, 2, 3, 4, 5, 6 edges, so I expect 6 to be my answer. My actual is going to be the static method from PS4, PS4 dot count edges graph. And then I want to use assert equals. I imported with the wildcard, so I have all my asserts already imported. Assert equals expected actual and we can run this. It'll be embarrassing if I got this wrong, but then I at least get to talk about debugging. So there's one test. Count edges empty. So let's create a graph with no edges. Now I expect 0. No edges. Let's do no edges. And here's where we get to use the add node method. So we're going to do graph, add node, and we're going to add a bunch of nodes to this graph, but no edges connecting them. So we're going to have a bunch of isolated nodes in this graph. I can't help myself but to add negatives, even though the values here are strictly nominal. They have no actual meaning. They just need to be different because we can't have duplicate nodes in our graph. So we're going to count edges. We expect that to be 0. And then I don't know. Simple. I don't really need another one. That first test case actually has us covered. The first test case is pretty complex. We should have a simpler one just for debugging purposes, but we're already past the complicated one. So let's make sure we got our edge cases. These are two good edge cases, no edges, but we have nodes and no nodes. So let's see if we pass these ones. And we do. So we did good. I did it right. Yay. But that's how we would work with these graphs for testing. Choose something for your type parameter, create a graph, add edges and nodes to it in a calculated way so you know exactly what you're expecting to have, and then set up your test case to check for it. And we could do the same thing with connected components. For example, this graph, this is a very good edge case for connected components. This is 1, 2, 3, 4, 5, 6 connected components in this graph. We have 6 nodes and no edges at all. That's 6 connected components that we have. So making sure that your connected components method is going to return 6 here. We have 0 connected components here, and I didn't pay too much attention to this. These are all connected to 1, 1 to 6 to 4. These are all connected. So here's one connected component and a second connected component. So this would have 2 connected components in this graph. So if you're counting connected components, this also has a cycle, 1 to 6 to 4. Oh, does it have a cycle? This might not have a cycle. 1 to 6, 6 to 4. No, this does not have a cycle. I spoke too soon. So no cycles in this graph. But we could add a cycle. Let's just change this to 4. So I don't break my number of edges. So 1 to 4, 4 to 6, 6 to 1, that's our cycle. Which kind of accidentally did most of the testing for you. And I think I'll skip the movie graph. This isn't going to be useful for our purposes. It's generating a graph from a file that has a lot of data in it. So if anybody has requests, I'll take requests right now. Otherwise, I think I'll just shut her down. It's got to be something else relevant. We did count edges. I just gave you all of count edges. I'm pretty sure those test cases I gave would cover all of the testing requirements for this one. I don't imagine I got more complicated than that in the testing. And then 4 more methods you got to write. Yeah, you're ready for all 5 of these with what we covered. I don't think we need to do the movie example and really talk about something that has nothing to do with these questions, since that's not what we're doing this semester. And that is trees is done, midterm is over and graded, async lectures recorded, it's out there for you. Uh, so this is it. This is my last lecture. Is there a way we can get bonus points in this course? No. Uh, no, just doing the problem sets on time can max out your points. That's the only way to get them. No bonus points. Yeah, and don't forget problem set 3 deadline tonight. 1 week. Problem set 4, and then if you need the final exam's there. That's everything. Like this is the summer. This is my last time going live. I think that's everything. No, I don't have any course eval incentive for the summer. Uh, there's you're looking for bonus points on these. I mean, there's just not. I don't know. There's just not a lot going on in the summer. Like there's so much more complexity to the grading. In the fall and spring, it's easier to do the incentives. I don't even know what I would give for an incentive for the summer. Just, yeah, no incentive in the summer. Summer just is what it is. All right. Anything else? Yeah. If not, that's it for me. Good luck on the remaining problem sets. If you have questions, post on Piazza. The TAs have office hours today. If you have your last minute problem set 3 questions. And the office hour schedule next week is actually going to be pretty different. I believe Miriam will still have her Thursday night office hours, but the rest of the schedule is a bit jammed up. We're pretty busy next week, which is why I have to have the async lecture. Next week is going to be a busy week. But you also have Piazza posts as well. You can post on Piazza and ask your questions there. And yeah. Good luck finishing up the problem sets. And if you need the final exam, good luck on the exam. I'll send out the emails to confirm to everybody what you need to do for the final exam. And with that, I'm done streaming. Lectures are all out there. Everything else is in your hands. I've done all the lecturing I need to do to get you ready for all the problem sets. So good luck, everybody. Take care. Enjoy the rest of your summer. I might see you IRL in the fall. I'll be teaching 220 if you're taking my 220 section. I'll see you there. Other than that, have a great summer and peace out.